Okay, we're going to go ahead and start working on part 2 of section 3.2.6. We're just kind of looking at ways that we can see triangles. Remember, in the real world, there aren't lines in the middle of the air to help you see this. So you've got to start seeing triangles, or how you can make triangles out of situations so you can use some of the things we've learned in geometry. Okay, here's some of the other examples, and for part 2 we are just going to give really a brief kind of a picture of how we might work on these. We had this one. I'm not going to read the story, but these are the measurements that they gave us and the diagram that they gave us. So they've done part of it for us. We can make this into a triangle by extending this down and extending this across. Now we actually have 3 triangles here, and some of our experience before would tell us that they're similar. What do all 3 triangles? Here's one triangle, here's another one, and here's another one. What do all 3 have in common? They all have that angle right there. So if I were trying to prove these were similar, I know that that angle has the same measure as that angle, the same measure as itself. Okay? Interestingly, what we talked about before, when things are going straight up to a flat surface, usually a level flat surface, it's a good bet that they're at 90 degrees. When he's standing, so he's at 90, we know this is going straight up. We hope that when they design this building, this isn't the Leaning Tower of Pizza, so it should be at 90 degrees. And so all 3 of these triangles have this in common, and they all have their right angles equal to each other. So I know that they're similar by angle-angle similarity. Now, let's set up some values. Let's use brown to show x is the distance from here to here. Okay, now I'm going to, I can't zoom in. Okay. Let's find x using these 2 triangles here. So I'm going to use the proportions, which I can use now that I know that they are the same, not same, similar. And I'm going to say that 6 corresponds to 2. And in the same sense, be careful here. This length here is x plus 12. 12 is what's in the drawing, x plus 12. So x plus 12 is that length, and then the shorter length is just x. Now let's cross multiply. Even though there's variables all over the place, let's see if we get something that's fairly easy to work with. 6 times x is 6x, and 2 times x plus 12 is 2x plus 24. Some really quick solving. 24 equals 8x. Divide by 8. Divide by 8. We'll get x equals 3. Where to put that? Right over here, so I have space for the other. X equals 3. So I'm going to plug that in right here. Now I'm ready to find out how tall Big Ben is. Okay, I'm going to put a little line here so I can just separate it. I see a little triangle, and here's its measurements, 3 and 2. Then I see the Big Ben triangle. I don't know how tall it is. Let's use a different layer. Let's use Y. But I do know how long this side is. It's 930 plus 12, that's 942, 945. So I'm doing this one and the big one. Okay, so let's go ahead, set up our ratios. Let's see, 2 on here matches the y, so I'm going to go y over 2. And I'm using the larger one on top, so this is going to be 945 over 3. Cross multiply. 3y equals 945 times 2, which is 1,890. Should have known that. Divide both sides by 3. And I'll get y equals 630. Okay, so how tall is Big Ben? It is 630. I believe that will be our marking. And that is this problem. $95. Okay, let's see. Okay, on 95, they asked us, let me review real quick, to show that, to find y, and then to show if these two lines are parallel. Now, I see two triangles here. I see a smaller one and a larger one. So let's look at them. I'm going to draw them separately so that I can kind of compare corresponding. And I'm drawing them in the same orientation just to make corresponding sides easy to find. This side on the little one is this side is 11. This side is 15. This side is 17. Okay. This one is 22. That one we don't know, it's y, and this is 30. Okay, looks to me like we have a good case that they might be similar. 11 to 22 has a zoom factor of 2. 15 to 30 has a zoom factor of 2. So we have at least two pairs of sides, so we can either try to use angle-angle or side-angle-side. I notice that both of these triangles share a common vertex or angle. They both share that angle right there. And so, I've got an angle. I've got the sides on the outside, so I'm going to say that this is similar by side-angle side similarity. So now I can use proportions. Okay, well I already know the zoom factor, scale factor is 2. So if this is 17, and I should be able to multiply that by 2 and get 34. If I did it the long way, I'd have 22 over 11 equals 30 over 15, and I'd multiply those out. Oop. 22 times 15, 330. 11 times 30, no, sorry, 11 times 30, you get 330. So you can see that they have the same scale factor. I could use that with this, then to say 22 over 11 equals 7 equals y over 17. Sorry, that's actually what I should have done first. And so if I bring that back over here, I'm going to get 11y equals 22 times 17, 374. Divide that by 11, and I get y equals 34. That's what we got there. Okay, now, you know that this is now equal to 34. Now we want to show that they are parallel. Okay, they're similar. So you know from similarity that angle H has to match up with angle A, and that angle R has to match up with angle K. Okay? If these two angles are the same, so this is like two lines cut by a transversal, their corresponding angles are the same, so that tells me that these two lines are parallel. Could also do it with these two, saying these two lines are cut by that one. And that's all the time we have, so good luck.